Okay, thank you very much. I'd like to first introduce Daniel Perot, Tycho Tracker, software for minor planets.
Thank you, Jerry. Okay, so hello, my name is Daniel Perot, and today I'm going to be presenting the Tycho Tracker software. This is software that's been developed for the detection and measurement of minor planets. And so one of the main features of Tycho is that it facilitates the discovery of asteroids. And so to that end, I would like to just provide a brief overview of the history of different detection techniques for asteroids, and then follow that up with a discussion on synthetic tracking. What is synthetic tracking? Why might you use it? And then also a discussion on advancements that have recently taken place to make synthetic tracking a viable technique. And then if you are interested in discovering asteroids, you might want to know what kind of criteria, what kind of factors to pay attention to. And so, again, just a brief history here on these detection techniques. So the blink comparator was first invented in 1904, and the most notable discovery was that of Pluto in 1930. And this technique works by taking two photographs of the same area of sky, taken at different times of the night. And by rapidly switching back and forth between these two images, it helps to make moving objects be observed. Now, it's not a commonly used technique today, simply because computer algorithms are more efficient at detecting these moving objects. And so in 1983, Tom Grills and Bob McMillan founded Spacewatch, and they were the first to make use of charge-coupled device technology, CCD camera technology, in discovering asteroids. And the way this worked was they would take 4 exposures, again, of the same field of view, typically 15 to 20 minutes apart, and then software would then automatically extract and remove stationary objects, such as stars, and then the remaining objects would be those of interest, the moving objects. And by and large, this is the technique still widely used today, even with the professional surveys. Now, another technique, and I added just this one here just because it's somewhat interesting, the Sloan Digital Sky Survey spends most of its time surveying galaxies and quasars, but it also captures sources in our own cosmic backyard. And so the way this works, it's fitted out with color filters. And so moving objects would be presented differently than stationary objects. So in the picture below, you can see in the left edge, there's a stationary object, a star, and in the center of that picture, you can see a moving object as it has exited from one filter to the next. Now, all detections require a minimum signal-to-noise ratio, and when that ratio is too low, the object appears indistinguishable from that of noise. And so all of the techniques that I've talked about up to this point are limited to the signal-to-noise ratio of a single exposure. In other words, they do not stack the exposures. So if you have a telescope or an instrument with modest-sized aperture, and you would still like to be able to detect those faint objects, then stacking becomes necessary. And so here you would then stack images with a motion offset. And this also helps to eliminate what's called trailing loss. So trailing loss is what happens when you have a longer exposure and the object becomes streaked. And so with the longer exposure, noise continues to build up, noise continues to accumulate, but the signal of the object is spread out across multiple pixels. And so the resulting signal-to-noise ratio is actually decreased with the longer exposure. So the way to mitigate that is to take several shorter exposures and stack them. Now, I'm sure most of us, or at least some of us here, are already familiar with this concept. There are different terms for it, but track and stack, shift and add, this is a concept whereby it's mostly used for follow-up, and that's because it requires knowledge of the motion of the asteroid in advance. So you have to know the motion of the object. Now, it does improve the signal-to-noise ratio, and the result is that the stars become streaked, and the tracked object then appears to be stationary. Now, again, this is not the same as using the mount to track the object, and instead you're still using sidereal tracking. You're still going to have the mount track the stars, but in software, in post-processing, the images will be, again, stacked according to the motion of the object. So here is an example of shift and add, and again, it's just one motion vector, but as you can see in the picture, the stars have become streaked, and the object itself appears to have been tracked. And so this is a great way to detect objects that would otherwise be undetectable, because here you're able to improve the signal-to-noise ratio. Now, the question is, let's suppose we still want to improve signal-to-noise ratio. Let's suppose we still want to detect these fainter objects, but we might not know their motion in advance. And so that's the idea behind synthetic tracking. And so that's the term used here. That's also called digital tracking. So it's useful, again, not just for follow-up, but also discovery, because it can detect objects having a wide range of motion. In other words, it's not limited to just one motion vector. It can explore thousands of motion vectors. And so the way this works is you start off with generating a trial stack for a particular motion vector. And it's called a trial stack because it is one of many stacks. And for each trial stack, you're then going to extract candidate detections. In other words, you're going to run an algorithm to identify objects of interest in that trial stack. And then for each candidate detection, you're then going to assign a quality metric to evaluate how good that detection is. And then you're going to do the above for, again, the thousands of motion vectors, however many you wish to explore, and then sort the resulting detections by quality, and then finally submit the resulting list for evaluation. So as an example, here you can see these are trial stacks of the same object. And so in the center here, this is what you would consider to be the correct motion vector. And then as you get to the edges, you can see that the motion is less and less correct. But these are all trial stacks that would be explored with synthetic tracking. And so it's a very, in fact, it automatically identifies the correct motion vector. So it's a very useful technique. Now, as you might imagine, synthetic tracking is more computationally intensive. However, in just recent years, it has in fact become a viable technique, even for amateur astronomers. And so here I'm going to go over the advancements that have made it viable, starting with the advancements in graphic processing hardware, and then the advent of full-frame CMOS cameras, and then finally the advent of large aperture fast focal ratio telescopes with Hyperstar and RASA. So in 2013, Dr. Shao of the Jet Propulsion Laboratory was the first to emphasize the use of synthetic tracking for asteroid discovery. Now, unfortunately, at the time, this was largely seen by others as impractical. They ran the numbers and said, well, it's too computationally intensive to be a practical strategy. But in 2013, the reference GPU, graphics processing unit, was a Tesla K20C. Now, that's not to be confused with the automotive company. This is a product of NVIDIA Corporation. So this costs $3,200, and it scores 12,000 on the CUDA benchmark. This is a benchmark that evaluates and ranks different graphics cards. Now, fast forward 7 years later, and now for $1,200, you can get a card that scores 162K on that same benchmark. So what I'm getting at here is that for almost a third the price, you can get computational processing power that's 13.5 times faster. It's an order of magnitude faster. I mean, this is enormous. I wish telescope optics could have the same kind of improvement and capability. So another advancement is that with full-frame CMOS cameras, so synthetic tracking works really well with short exposures, and I define short as being 30 seconds or less. However, short exposures tend to require low readout noise, and CMOS cameras happen to have that, but traditionally they've been available with just a very small sensor area. But just in the last year, Sony released the IMX455 sensor, which is 60 megapixels, true 16-bit, and it's available in 2 different cameras. for the amateur astronomer. Now, another advancement here then, of course, is availability of large aperture telescopes, fast focal ratio. So Hyperstar has been around for a while, but Roe Ackerman Schmidt astrograph, that's relatively new. So Hyperstar is a sort of a modification to an existing telescope. It works with a normal Schmidt-Cassegrain telescope. It achieves f1.9 focal ratio. ROSLA is optimized for imaging. In fact, you cannot use it for visual purposes. It has f2.2, and on paper, the advantage it has over Hyperstar is it offers a larger imaging circle. So, okay, let's suppose you are interested in discovering asteroids. So what kind of criteria, what kind of factors should you pay attention to? So first, you have limiting magnitude. You really do need to detect those fainter objects. And of course, you have to have good sky coverage. And then finally, the cost to achieve the above. So we want this to be a cost-effective survey. So limiting magnitude, synthetic tracking enables a C14, that's a celestron 14-inch telescope, to regularly achieve magnitude 21. And this is shown by astronomer Mark Holbrook, who I've collaborated with. And the question is, how important is limiting magnitude? So as an example, we have two survey telescopes, 703 and G96 at Catalan Sky Survey. So 703 has a larger field of view, 20 square degrees versus 5. So on paper, it should capture 4 times as many discoveries, but in fact, it only captures 1/5 as many. So why is that? Well, 703 has a limiting magnitude of 19.5, whereas G96 has limiting magnitude of 21.5. So 2 magnitudes makes quite a difference. And you can see that on the chart here. So this is a chart of number of discoveries per survey in calendar year 2019. So F51 is Pan-STARRS, that's a 1.8 meter telescope. They reach magnitude 22.7. And I just talked about G96. F52 is also Pan-STARRS, but they're a new installation just coming online. 703, I just mentioned them as well. And TO8 is Atlas. So Atlas is well known for having a good sky coverage, high cadence, but they only reach magnitude 19. So limiting magnitude is important. Of course, by itself, that is not sufficient. So you must also actively scan huge portions of the sky. Now, nothing is free. So synthetic tracking will give you that limiting magnitude, but to do so, it takes a longer dwell time. Now, the solution is to use an array of telescopes. Now, you might think that's going to blow the cost part of the equation out of the water, but let's take a look at that. So cost of aperture increases exponentially with size of mirror. I would love it if a 1 meter telescope simply cost twice as much as a ½ meter telescope, but that's simply not how it works. So let's take a look at an example here. So G96 versus an array of modest-sized aperture telescopes. So G96 takes 120 seconds to capture 4 30-second exposures, and each field is again 5 square degrees. So therefore, it has an efficiency of 120 seconds for that 5 square degrees, and that works out to 24 seconds per square degree of sky. Now, if we wanted to have an array of modest-sized aperture telescopes, let's start with just one of those telescopes. So a single ROSLA 14 paired with an IMX 455 should reach comparable magnitude in 790 seconds. So we said G96 will reach its magnitude in a 30-second exposure, because again, those exposures are not stacked. And here we're going to take 790 seconds to achieve comparable magnitude. So, and with that sensor, it will achieve 4.5 square degrees and have an efficiency of 176 seconds per square degree. So that being said, if you had an array of 8 of these instruments, then that should work out to an efficiency of 22 seconds per square degree. And if you figure out the cost of this, let's suppose some budgeting for mount, camera, and telescope, it's $30K per instrument, and then 8 of those, 240. And then you budget for computing hardware, and then finally say $500,000 for a roll-off building to house them. You're still under $1 million, and that's still an order of magnitude more cost-effective than a custom 1.5 meter instrument with a custom camera. So example here, as you can see in this diagram, we have a roll-off building, again, to house this array. Roll-off building is very efficient for this purpose. And so again, Tycho Tracker, this has started development in 2018, and it also supports, in addition to synthetic tracking, you can generate light curves, determine rotation periods, identify orbit linkages, and of course do follow-up observations of asteroids as well. And so just some examples here with photometry, if you're interested in that with this tool. Here's a raw plot of asteroid 18172, and if you wanted to determine its rotation period, it has a period search module, and then it will show the phase plot diagram of that, and then a periodogram, so you can determine period spectrum and so forth. And so this is a tool that's now in use by several observatories, and I list a few of them here, and then a link to it below. And so at this time, if there are any questions, I'll be happy to take them.
Thank you very much, Daniel. Have you seen any questions, Wayne? You're muted, Wayne.
Hi, Greg. I've just unmuted your microphone. Do you have your question?
You have, perhaps. Can you hear me?
Yes.
Oh, cool. Yeah, I would just, we've exchanged some communications in the past, Daniel and I have but it's been quite a while. I have a 1060 GPU instead of a 1080. Will Tycho run on that, or does it require a 1080?
Well, when I first developed Tycho, I actually developed it with a GTX 970 card. That's an older card.
Yeah.
Yeah. And so it should work with that. The main consideration is the size of the data set that you wish to process. So you want to look at the video memory and so forth.
Okay, thank you.
Does anyone else have a question? Here we got a couple, let's see, no more raised hands that I'm seeing.
Yeah.
Any questions,
Yes.
panelists?
I do actually have a question. This is Greg Sivikoff. Can you
Okay.
hear me?
Yes.
Excellent. So as more and more GPU needs get increased, do you see any possibilities of developing a service where people could use cloud GPUs as opposed to their own GPUs to make this more accessible to people?
Sure. Actually, I have experimented with a Google Compute Engine. So you can spill up a virtual machine, and in fact, with that, presently they offer a V100 GPU, and that's a very high performance GPU. So in essence, you can actually do that today. You could load up the Tycho software on Google Compute Engine, and again, you would basically be renting time on Google to run their cloud services. So that's kind of one thing that's already available.
Thank you.
Wayne, I see
have
George Lawyer has his hand up.
Yes. Okay, George, I'm going to go ahead and I'm opening your microphone.
Hi, just wanted to ask, I'm looking through the paper and didn't hear anything about how you find the software. Interested in using it and working with some of the folks at my observatory to try this out.
Sorry, what was the question?
How do we find the software? How do we get the software?
Oh, okay. Well, the website is tycho-tracker.com. There should be on the PowerPoint at the very second to last slide, I believe, was a link to it.
Oh, okay, missed that. Okay. All right, thank you.
Thank you.
Any questions from any of the panelists?
Well, Pablo and John Hood have raised their hands. Let's open the microphone for Pablo. Hello, Pablo, do you have any questions for us?
No, I have a testimonial because I've been using that program for a couple of months now. It's just amazing what you can do with it. I've been discovering in my old data all kinds of NEOs and not new, but I've been able to track already reported NEOs and comets and everything else. And it's extremely easy to use. And as long as you have a GPU, it's quite fast. And I've been going back 4 years of data that I have 4 years. And if you go to his website, he has videos that explains everything on how to do it, how to report to the Minor Planet Center. It's amazing. It's an amazing program, the capability that it has. That's all I have to say. And I'm a low-level astronomer, amateur astronomer, no astronomy background other than what I've been doing as an amateur astronomer. And you can use just about any telescope and any old data, you can discover all kinds of things. It's really an amazing program.
Thank you, Pablo.
Okay, and John Hoot.
I was curious if anybody has run this on AMD iron.
Yes, I have received from some emails. There are some folks who have had success with the AMD, and so in theory it should work on an AMD platform.
Does that include AMD accelerators or just the cards listed on your web page?
It would include AMD accelerators, yes, the AMD GPUs.
Excellent.
And it uses the OpenCL API. So CUDA is more NVIDIA proprietary. But OpenCL is supposed to work with both NVIDIA and AMD.
Okay.
Okay, and we have another question from John Murrell. What does the software detect satellites, and what's going to be the impact of Starlink?
Good question. So yes, it can detect satellites. I have an example of actually a near-Earth object, but it was moving at 1164 arc seconds per minute, and that's actually faster than a satellite in GEO. So a geosynchronous satellite will move 900 arc seconds per minute. In other words, I believe 15 degrees per hour. So if it can detect the NEO, in that case, it'll certainly detect the satellite. Effect of Starlink, that's actually one of the advantages of synthetic tracking, is that because it makes use of many exposures. It doesn't matter if one of the exposures is quote unquote bad. If you have a Starlink footprint or trail, and even a couple of those exposures, it's not an issue, because synthetic tracking, typically you'll take again 30 to 60 exposures per field. So it's kind of like what amateur astronomers do with astrophotography. Again, you'll take numerous exposures, and you can do some filtering. You can exclude just the small handful of exposures that have some artifacts in them.
Okay, Jerry, I think we should probably get back on with the program here.
Daniel, thank you very much. This is very intriguing stuff.
Thank you, Jerry.
Thank you.